Okay, good morning, everyone, and welcome to our fifth speaker for the joint seminar series between Binghamton University and Vellore Institute of Technology. Dean Vasudevan and myself are delighted to co-host this webinar series, and thank you for participating in this seminar. Today, we are very delighted to have Dr. Fuda Ning, who will talk about additive manufacturing for metal parts and complex structures. Just a quick introduction about Dr. Ning. He joined the Department of System Science and Industrial Engineering at Binghamton University as an assistant professor in the fall of 2018. He received his bachelor's and master's degrees in mechanical engineering from Dalian University of Technology, China in 2011 and 2014, respectively. Then he received a Ph.D. degree from the Department of Industrial, Manufacturing, and Systems Engineering at Texas Tech University in Lubbock, Texas, in May of 2018. His research interests include laser-based and extrusion-based additive manufacturing of high-performing and multifunctional engineering components. He has more than 60 academic publications and is a member of IISC, ASME, and SME. So please join me in welcoming Dr. Fuda Ning to this webinar series. And thank you again for your participation. Dr. Ning, I'll turn it over.
Okay, thank you very much, Professor Kasani, for your invitation. And so that I will be very happy to present my research in this joint seminar between the Binghamton University and the VIT. And good morning and good evening to all the colleagues in BU and VIT. So again, my name is Fuda Ning. I'm the assistant professor at the Department of System Science and Industrial Engineering at Binghamton University. Today, I will be more than happy to present my research area in additive manufacturing and talk about the detailed projects that have been conducting at Binghamton University here. As Professor Kasani just introduced, that I joined the Binghamton University in 2018. And I created and established my research lab, which is Advanced Materials and Additive Manufacturing, as also abbreviated as the AM2 lab. So some of the detailed projects and the research update and some of the fantastic research news can be found in this research website here. So overall, my research focused on the development of advanced materials and novel processes during additive manufacturing of the metal and composite materials. We look into the relationship among the processes, structure, and properties. And here in this slide, I'm going to show you the overall picture of the research activities in the AM2 lab. So again, our research goal is to uncover the fundamental relationship among these four aspects. And we look into the fabrication of high-performing and multifunctional parts that can be utilized in the aerospace and biomedical industries. So basically, we can divide the AM paradigm into the two categories. The first one is the extrusion-based additive manufacturing, where we utilize the composite materials to fabricate the continuous fiber reinforced plastic materials. And this is actually the topic that I'm going to present today. And the second one is the metal fabrication utilizing the extrusion-based technology, where we can start with the FDM process to extrude the grain metal parts, and then we can debind and sinter the grain part into the fully densified metal materials. So that's also named as the ES AM process. The other one is the hybrid additive manufacturing. As some of you know, that hybrid has becoming the disruptive and promising technology recently, where we can also equip the multi-axis, like four axis or 5 axis, to allow us to fabricate a complex materials on the non-planar or irregular shaped substrate. On the other hand, we also look at the interaction between the laser and the materials, which in both the powder forms or wire forms. So we can print pure metals or matrix composite materials, and we characterize the underlying thermodynamics and also the structural and mechanical performance of the part that we fabricate. So again, these are the overall projects that have been conducting at Binghamton University here. And without any further ado, I would like to move forward to the topic today, additive manufacturing of continuous CFRP composites. We will talk about the fiber matrix impregnation behavior and also how to predict the tensile property by utilizing a physical or a mechanistic model. So I varied this topic from the metal parts to the composite parts, as we recently published 2 papers in the additive manufacturing journals. And I think this is a really good chance to share our research findings and disseminate our research to all the colleagues and scholars in both United States and India, so that we can have some potential collaborations. And also I highly recommend that all the scholars and students to read and cite this paper if your research fall into this area also. So I'm going to introduce the background and motivation of this work, and then talk about how we develop the models to unveil the underlying impregnation behavior and how to predict, generate the prediction of the tensile performance of the part. And then talk about experimental conditions and measurement procedures, and also the results and conclusion of this work. So the CFRP, the carbon fiber reinforced plastic, is a very advanced composite materials that consist of the carbon fiber as a reinforcement and the resin polymer as the matrix. And such a composite material exhibit a low density, high strength to weight ratio, high stiffness to weight ratio, and high fatigue resistance. So those superior mechanical and physical performance enable the CFRP to be widely utilized in the aerospace and aircraft industry. For example, in the aircraft industry, if we can reduce the weight by 1%, the fuel consumption could be reduced by 3 to 4%. So that's a huge improvement in the fuel consumption reduction. Whereas in the aircraft launching, for example, if we reduce the weight by 1 kilogram, we can certainly increase the launching range by 18 kilometers. So those examples indicate the key function of the CFRP and also their associated outstanding performance. So how to fabricate CFRP traditionally? Let's look at the manufacturing processes on the top. So the first one is the automatic placement. In this process, we can employ the robotic arm to deposit the CFRP onto the huge substrate, so that we can build a very large component, and then later on we have to place such a component into the autoclave furnace for the molding and compression process. The welding is another method to fabricate the cylindrical part. and also the protrusion process, where we have to apply both carbon fibers and the resin, liquid resin, to form into the prepreg, and then we have to mold this part into a solid material as well. So those are the traditional manufacturing methods, and as you can see, they are really powerful in making the huge and large component that can be utilized in the energy and space industry. However, in some of the other applications, such as automotive or the turbine blade parts, some of the complex geometries, such as the curved surfaces, non-planar geometry, some of the folds and other irregular geometries of the part. So as you can see, the demand for the CFRP with a complex structure is increasing nowadays. During the connection of the part or the fabrication of CFRP, we typically fabricate the individual parts, and then we have to assemble those multiple parts into a huge component. So we can employ the gluing or bolting or the laser welding process to mount those parts into a huge component. For example, laser welding, we can employ the CFRP and also the metal substrate to allow us to generate the stack materials. For example, the CFRP titanium stack material, the CFRP aluminum stack materials. So in this process, the laser can weld the interface or can generate high temperature through the heat conduction to melt the interface so that the part can be stacked by each other. However, during those connection or assembly process, we'll expect to see some potential problems, such as the delamination or the weak joints will always occur in this process. So how to solve this problem, how to improve the interfacial bonding, or how to develop a novel process to fabricate the composite material is a very key research task. So that's the reason that we employ the additive manufacturing for this project. And by keeping in mind that some of the audience or students may not familiar with additive manufacturing, I'm gonna just briefly talk about what is additive manufacturing. So this technology has been developed by many years, and it is a joining process. Like we can join the parts layer by layer, and that's opposed to the subtractive manufacturing methodology, such as the machining process. So that's a layer by layer methodology. And specifically, we have to design the three-dimensional CAD model by either utilizing the Fusion 360 or Creo programs. And then we have to convert the CAD model to the STL file, which is the only format to be recognized in the 3D printing process. And then we have to slice the part into different layers and generate a G code. We can fabricate a part by feeding the feedstock materials in a variety of additive manufacturing processes. So this is the overall process. We start from the CAD model to the the specific process that we employed is called fused filament fabrication or fused deposition modeling. So in this process, we can employ the thermoplastic or thermoplastic matrix composite materials to fit into this liquefied head. So in this extrusion head, we have the nozzles to fully melt the thermoplastic, and then we can deposit part layer by layer. And this is the equipment that we utilize, but we have to modify the extrusion nozzle and the extrusion head to allow us to fabricate the composite materials. So in 2015, 5 years ago, we are thinking, can we increase the mechanical performance of the pure thermoplastic? Because at that time, we only have the access to the pure thermoplastic, like ABS or PLA or PC. It's not like the options of the materials nowadays, right? We may have a lot of various options of the materials, like a carbon fiber or a graphite, or even the copper reinforced polymer. But back in 2015, there are few options other than the pure polymer. So the motivation at that time is to you know, add some carbon fiber as the reinforced material to seek the potentials of increasing the tensile, flexile, and compression properties of the part. So we published a couple papers, and it has been cited about 1,000 times in these related publications since 2015. At that time, we utilized a short carbon fiber to reinforce the materials, and we print both tensile and bending specimens and investigate what's the effects of the carbon fiber content on the overall strength performance. So as you can see from the previous result, that we can somehow increase the ultimate tensile strength by about 40 to 50%. We also characterize the interfacial morphologies, and also we have to check what is the porosity and voids of the part at that time. But basically, you have to keep in mind that those mechanical performance have to be further improved, because we have to think about how to utilize the part in the real industry, such as the aerospace sectors. They require a very high level of those tensile strengths. Another potential issue of this short or chopped fiber is that it's really difficult to control the fiber distribution and orientation during the printing of this process, because the short fiber can be distributed randomly, but our object is to locate those or orient those fiber in the vertical direction, so that we can generate a higher load-bearing capacity. So that's why we moved to the continuous carbon fiber. And nowadays in the market, we have the Markforged company, which produce the Mark I and Mark II printers, and they utilize the continuous carbon fiber or the continuous glass fiber to serve as a reinforcement. And as you can see, they can increase the tensile strength to about 150 to 200 megapascal. And even we can further increase the tensile performance by the post-processing heat treatment. So this is the comparison in terms of the tensile strength among the pure plastic, the short carbon fiber, and continuous carbon fiber. But we developed the process in another way. So first of all, if we look at the different ways for the fabrication of continuous carbon fiber, the Markforged printer, they employ the dual nozzles. One nozzle is to deposit the thermoplastic materials as the matrix, and the second one is the continuous fiber in a separate nozzle. So these are the commercial machines. So the way that we are utilizing is the coaxial extrusion. So that's being said, we can insert a continuous fiber together with the two feeding of the thermoplastic polymer into the single nozzle. So the benefit in this way is to enhance the fiber matrix interfacial bonding in the during the extrusion process. So this is one of the advantages, and we can of course tailor the volume percent of the carbon fiber in this way. Now I would like to give you some literature overview in this field. So as you can see, some of the scholars have investigated the modification of the surface of the feedstock materials before they feed into the printer, so that they can somehow tailor the surface roughness and of course the surface property of the materials. And they figure out that the tensile strengths and flexural strengths can be increased. The effects of a process parameter on the compressive strengths have been also investigated. They look the cell length, the layer thickness, and the core density effects on the overall compressive property. Some other investigation talk about the relationship between the impregnation behavior and the mechanical strengths experimentally, and they figure out a better impregnation behavior can definitely enhance the mechanical behavior. So now we are thinking how to quantify and characterize the fiber matrix impregnation behavior based on the research gap. We really want to know what's the underlying behavior during the CFRP fabrication. So we employ the Darcy's law and the polymer rheology and look into this macro mechanical model to review this mechanism. And the second research question is in this work is, hey, once we print the continuous part in this novel process, can you predict the tensile performance? Can you estimate the strengths utilizing a physical model? So that's the motivation of the second research work. So basically, we developed this model from three aspects. The first one is the characterization of the fiber property, how to predict the strengths of the fibers, which are in two detailed categories later. The second one is the matrix material performance, as we utilize different thermal polymer. So how to quantify the performance of those polymer. And the very last one is the experimental measurement for some key factors, as there are some gaps and orientation coefficient. So we have to characterize what's the value of those coefficients or the attributes of the carbon fiber. So we experimentally measure those and integrate into our models. And I'm going to talk about this later on in the modeling process. So first of all, before the model development, we have to give some assumptions. So the first one, in the carbon fiber bundle, which consists of thousands of monofibers or monofilament, we want to know what's the relationship among those monofilament. So here we assume that the monofilament is identical to each other in terms of the shape or the size of the diameter. The temperature distribution within the nozzle is uniform during the printing process. The melt of the matrix is incompressible fluid because we have to characterize the fluidity and the viscosity of the thermoplastic later on. The impregnation process primarily and uniformly occur at the orifice because we investigate the printing process and figure out that the nozzle will certainly generate the pressure and the squeeze the molten thermoplastic on the platform. So that's the the major region where the impregnation take place. Impregnated carbon fiber will not debound from the matrix, and also the assumption regarding the cross-section of the impregnated carbon fiber toe. So we assume it to be in the elliptical geometry. And then we move to the first one, which is the modeling process of the impregnation behavior. So now we employ the Darcy's law to characterize or to build a relationship between the pressure of the nozzle on the melt materials and the viscosity of the thermoplastic. And also we specify the viscosity by utilizing the polymer rheology methods. And we convert or generate the expression of the attribute X, so which is the depth of the impregnation. I'm going to highlight this in the next slide. But here we can obtain the final impregnation distance. So the impregnation distance X is the thickness of this elliptical ring, which indicate the impregnation zone between the matrix and the carbon fibers. So now we utilize the impregnation percentage to define the overall impregnation behavior, which is the ratio of the impregnated carbon fiber toe area in red, and also to the overall area of the cross sections of the carbon. So this is the calculation of the impregnation percentage, and we of course build this equation based on a couple of assumptions that I just mentioned. So after we develop the models for quantifying the carbon fiber and the matrix impregnation behavior, we move to the prediction of the tensile performance of the part, because that is the key attribute to represent the overall performance of the part that we fabricate, right? So we develop the modeling process by the rule of mixture at the first step. As you know, the composite materials have both the reinforcement phase and the matrix phase. So the rule of mixture is a very important equation that we can initiate by divide the material into both the fiber part and also the matrix part. So we can calculate the sigma, which is the yield stress for doing the tensile testing, and also the elastic of modulus. So this is the original equation. But here in our scenario, we have to think about the physical gaps, for example, in the interface of the part. And also there are a lot of voids and porosity in the part. So the gap ratio have to be measured. And of course, the carbon fiber has to be divided into the two categories. One is the impregnated carbon fibers, and the other one is unimpregnated carbon fiber in the inner side, because it is inevitably generated during the pressing of the matrix. Only a portion of the matrix can be wrapped around the carbon fiber. Another factor is regarding the carbon fiber orientation or direction. So theoretically, it is in a horizontal direction when we lay those material down to the platform. However, in the actual printing process, some of the continuous carbon fiber may be disoriented, and we have to calculate what's the overall coefficient to represent the orientation angle. So we modify the RM equation by considering the aforementioned characters. And then we have to calculate the sigma sub F1, which the carbon fiber in the unimpregnated status, and of course the sigma F2, which is the impregnated carbon fiber. So we calculate separately. The first one is the tensile strength of the unimpregnated carbon fiber, sigma F1. We consider that the failure of the carbon fiber follow the Weibull distribution, and we start with the tensile strength of the monofilament. If you remember, there are a lot of monofibers in the overall carbon fiber bundle. So we have the order of those tensile strengths, okay? And then we calculate what's the overall tensile strength of the carbon fiber bundle, which may consist of thousands of monofibers in it. So this is the first step, that we calculate the sigma F1, and then move to the sigma F2, which is the impregnated carbon fiber tensile strength. We conduct analysis from the relationship between the fiber and the matrix. We conduct the shear lag analysis, and the equation is also based on the Hooke's law, so that we can build a relationship between the carbon fiber, fragmented carbon fiber, and also the unfragmented carbon fibers. So this is the calculation of the sigma F2. And as I mentioned, once we have the F1 and F2 in the property of carbon fibers, we experimentally measure some of the key factors, as I mentioned, such as a gap ratio, the fiber orientation coefficient, and also we have to know what's the corresponding volume fraction for those impregnated fibers and the impregnated fibers. And of course, we characterize the matrix stress and matrix modulus as we utilize different thermoplastic as the matrix materials. So that's the overall model development. And once we have all those factor obtained, we can finally achieve the tensile strength and elastic modulus of the as-built part. So what are the experimental conditions that we utilized? So first of all, for the carbon fiber, as I mentioned, that is a carbon fiber bundle which consists of thousands of monofibers in it. We employ 5 different thermoplastic resins, including the PA, PC to the short carbon fiber reinforced PA, which contain 25% of short carbon fibers. So we really want to know what's the effects of those thermoplastic on the overall performance of the composite materials. And this is the actual experimental setup, where you can see the carbon fiber bundle will be fed into the nozzle, and we utilize the 2 thermoplastic feeding paves as we want to eliminate the effects of the feeding direction of the thermoplastic into this system. So this is the overall continuous CFRP part, which is in the black color on the platform. As you can see that these are really solid materials, and we experimentally measure the performance later on in the next slides. The experimental process parameter cover the printing speed, the nozzle temperature, the layer thickness, and we employ different levels of the process value. I mean the parameter values for each category. And this is the infield pattern, which is the concentric mode, where we start from the very first layer, move into the center portion, and then we start from the center to the outlier contour. And so the part can be printed layer by layer in this mode. And this is the geometry that we utilize for the testing process later on. if you remember that we have to experimentally measure some of the coefficient of the thermoplastic. So we employ the one of the rheometers to measure the viscosity. And of course, we applied a wide range for shear rate and temperature as well to detect what's the relationship between these two parts. And also we want to obtain a wide range of the values, and we can later on fit those values into the coefficient calculation. On the other hand, regarding the impregnation percentage, once we have the theoretical model and prediction, we want to verify if the predicted result is correct or not. So by characterize the cross-section of the part, we can compare the experimental data with the theoretically predicted data, right? So we, first of all, section the part to review the cross-section of the materials, and the impregnation percentage was characterized by the ratio of the extracted impregnation area in red color to the total cross-section area of the actual fiber toe in this case. And later on, we have to measure what is the gap ratio and also the unimpregnated carbon fiber. So this is the image processing. We conduct the binary conversion with two different thresholds so that we can have the information for the gaps in black here, and also the overall area of the gap and the impregnation carbon fiber. So we can obtain what is the unimpregnated carbon fiber area in this way. So again, this is the actual measurement process to verify the theoretical modeling data. And in addition, we measure the fiber orientation coefficient. Keep in mind the carbon fiber can be in different directions. Most of the carbon fiber will orient in the 90 degree, which is in the horizontal direction in this image. And some of the fiber, as you see from this actual image, could be located in different orientations. So we utilize the image processing to obtain such a coefficient K to represent the overall orientation behavior. Of course, the tensile testing has been conducted to measure what is the experimental data of the tensile behavior. And here we obtain those experimental results. As you see, the first one is the rheological property, including the consistency of the fluid and the power law exponent n. So those are the coefficients that we utilize during the theoretical modeling process. And then once we have the predicted data, we want to compare with the experimental results. And as you see, we conduct the printing by changing the nozzle temperature, printing speed, layer thickness, and the predicted trend of the impregnation percentage were consistent with the experimental ones. And almost all the predicted data agree well with the experimental results, whereas some of the location indicates a little bit higher variance between those two set of data. This is because of the assumption. If you remember, we utilize a couple of assumptions at the first beginning, and in the actual printing, we definitely expect to see some variance because the printing may have a more complex conditions than the assumptions. And later on, we want to know how we can further improve this verification accuracy in the future work. So now once we verify the impregnation behavior, we want to know what is the accuracy of the tensile performance prediction. So first of all, we calculate the coefficient K, and for different thermoplastic, the K value is a little bit different. For example, in the PRA-based carbon fiber, the orientation of carbon fiber is about 94 to 95%, whereas for the PA matrix, it could be 92 or 93%. So that somehow varied the prediction result at different matrix combination. And as I mentioned, the matrix strengths and the elastic modulus should be characterized as well. So if you remember, we have 5 different metrics, and we characterize the stress to strain curve, obtain the elastic modulus and yield stress for each category. And then by utilizing those information and also the modeling equations, we can definitely predict the ultimate tensile strength of the carbon fiber reinforced materials. We utilize the UTS, ultimate tensile strength, elastic modulus, and failure strain to represent those tensile behavior. And as you see, once we compare with the theoretical results, we can calculate the relative areas between these two parties, right? And in terms of the ultimate tensile strength, the error has the range from 2.8% to the larger one, 4%. This is a relatively a good agreement. For the elastic modulus, the largest error could be 8% in the first 2 categories. So these are the model verification for the strength model. And lastly, I'm going to just briefly talk about, the conclusion of this work. So again, we firstly unveil the impregnation behavior in the CFRP parts fabricated by this novel co-extrusion FDM process. And also we develop a model step-by-step to predict what is the tensile strength and also the elastic modulus of this continuous carbon fiber. So somehow this project provide the insight into the relationship among the materials, process, impregnation behavior, and of course, the resulting mechanical performance of the part. So I think this is the very last slide of this presentation. I would like to take any questions that you may have. Thank you so much for your attention.
Dr. Ning, thank you very much for the nice presentation. It was great that you have showed an overview of the infrastructure that you have in your lab for research in the various domains in additive manufacturing, and also the short introduction about the additive manufacturing technology, especially because I noticed that we have quite a few students in attendance. So for those that do not have the background, this is definitely a great introduction to the fundamentals of additive manufacturing, and then giving them one application of a research area that you are currently involved in. So this was very, very nice. Thank you very much. So at this point, we can open it up for questions from the audience. Feel free to unmute yourself and ask the question. Or you can type it in the chat and I will read it to my colleague, Dr. Ning.
Good evening, Professor. I had a question. I am Professor Raja.
Hi.
Professor Ning, have you done any XPS studies for impregnation of these 2 materials? At what orientation? What is the bonding strength or bonding energy between these two materials at the different orientation we had impregnated, right?
Yes. So in terms of the bonding strengths, that at this time we just characterize the tensile strengths of the overall part, and the bonding strength is very important as well. But now we just characterize, what is the impregnation percentage strategically to unveil the sort of bonding adhesion performance between these two, two phases. But that's a good point. We can definitely characterize what's the bonding behavior by experimentally conducting the shear testing or the peeling test.
And how about the residual stress? Residual stresses because of this bonding.
So you're asking about how to calculate the stress of the bonding?
Yeah.
So actually, when we conduct the shear test, if we have one party as the carbon fiber, another party as the matrix, and we can definitely have the shear test to indicate what's the shear stress of the part. And also, if we want to characterize the peeling behavior by, I would say, have the vertical testing of the part so that the carbon fiber can be delaminated from the matrix, so that we can indicate or characterize what's the peeling behavior from that way.
Thank you, Professor Ning. It's very interesting work.
Yeah, thank you. Sure.
Thank you. Dr. Ning, we have a question from Danosh Patel. The question is, did you come across any warping or geometric distortion due to residual stresses? Since the overcured CFRP laminates do experience warping, what effect can be seen in case of extruded CFRP samples?
Yeah, that's a good point. In terms of the warpage or distortion, so for now, all the samples that we have printed experience very little distortion. If I go back to the previous experimental setup here, if you look at the overall sample that we're printing, this is a really large size, and we experience very little distortion. But in terms of how to avoid the distortion, or how to generate the part with a better accuracy, you have to definitely control the nozzle temperature, or we have to preheat the platform so that the thermal gradient could be reduced, so that we may decrease the reduced stress. Somehow we can prevent those distortion happening. I'm not sure if I answer your question.
Okay, thank you very much, Dr. Ning. I will wait to see if there are any. Yes, our colleague says yes. Thank you.
Okay, thanks.
Acknowledge the answer. Yes. Any other questions? Again, please do not hesitate to unmute yourself and ask the question, or type it in the chat. There's a question from Mr. Kumar Raja asking about, can we do ultrasonic welding of CFRP?
Yeah, definitely. That's actually one of my previous investigation by utilizing the ultrasonic vibration technology. So in terms of the CFRP fabrication, if we have to consider the utilization of ultrasonic, we may have to prepare the CFRP material in the pre-preg form. So that's kind of the very thin sheet of the CFRP, and then we have to lay down the CFRP pre-preg onto the substrate layer by layer, and then ultrasonic will be utilized to consolidate the part. So that's not a melting process, but that's a consolidation process. And in addition, you may know the ultrasonic has been utilized in the laser-based additive manufacturing, such as the direct energy deposition. And you can also see the wet application from that research field.
Thank you, Professor. Just I seen in the direction of plastic welding process.
Yes.
Thank you.
Okay. Dr. Ning, there is a question about how to get an idea that which orientation would be more suitable for conducting the research, and can we extend such work for other synthetic fibers?
Yes, definitely. So if we look at the part and fabrication, of course, if we have the orientation parallel to the testing direction, that will be the best, right? That will be generate the highest load bearing capacity. And another factor you have to consider is that during the fabrication, we may have to generate the multi-directional part rather than the unidirectional composite materials. As you know, the multi-directional composite material will exhibit a larger mechanical behavior in different direction rather than in the only direction, right? So that's the actually the actual application of composite material in the industry. Somehow they want to print the part in multi directions. But again, if you want to achieve the goal of the highest tensile strength, for example, in the vertical direction or in the 90 degree, so during the printing, you may have to think about parallel your raster angle in that direction.
Okay, great. And we also have another question from Danosh Patel about the quasi-isotropic nature of these AM parts. Can it be achieved using the extrusion method, and where your tests uniaxial or biaxial tensile loading?
So let me just double check the chat window regarding this question, because I'm not quite clear about this question. So the quasi-isotropic nature of those AM parts can achieve using extrusion method. So to be honest, I'm not very clear about the quasi-isotropic, testing at this time. But of course, we can definitely try to have the, the biaxial tensile testing for the CFRP material. I think this is a really good point. To the best knowledge of mine, I don't think there are any biaxial testing at this moment for the CFRP. So this is a really good research gap and the direction in the future. I will definitely look at into it in the future. But biaxial testing for CFRP could be really practical in the industry. For example, in the defense industry, right? Because the key component could be experiencing the impact from the biaxial direction, not just the uniaxial direction. That's a good point.
And Dr. Ning, also have a question from Dr. Mohan Kumar. Is it possible to simulate in 3D the polymer flow with continuous fibers through the nozzle?
Yeah, definitely. I think there has been, I think one or maybe two publications in this area to simulate, the flow ability or the flow behavior in the nozzle during the fabrication of the CFRP. So, yeah, that's definitely possible to do that.
Yeah, and Dr. Mohan Kumar also added that short fiber plus polymer flow were modeled using the Brownian motion principle and some flow models. Can we look for a method for continuous fiber plus polymer flow?
Definitely, I would say that we can, develop a method to, simulate those, the interface or the interfacial behavior between the continuous fiber and the polymer during the fabrication. Yeah, that's a good point at this time. But what we modeled is the only the interfacial behavior at this time, because we really want to know how much portion of the matrix can be wrapped by the carbon fiber, and how to quantify this impregnation behavior. So that's basically what we have done at this time. Yeah, but that's a really good point, to develop this polymer and continuous fiber flow in the future work.
And Anoj is asking, how do you manage the extruder to print two different materials in specific proportion continuously?
Right. So let me go to the maybe the schematic of the methodologies. So here, if you look at the carbon fiber, that has to be pre-placed into the nozzle head, and then once we have the carbon fiber printed on the build platform, due to the driving force, this carbon fiber will be automatically printed continuously. So this is the overall printing process. We have to insert the carbon fiber first, and later on have the thermoplastic feeding into this single nozzle. But again, as the carbon fiber has been created on the platform, right? So it will be somehow as the dragging force to direct the subsequent carbon fiber.
Okay, thank you, Dr. Ning.
Professor Ning, I have a question.
Yes, please.
Hi. On this, you had shown that there is a build platform. I wanted to know whether the CFRP gets integrated into the build platform, or if there are alternatives. For example, is it possible to make a sandwich of a CFRP on a metal, and then again metal on the top of it, so that it works like a metal matrix composite? Could you please give some ideas, give some details about it?
Yeah, sure. So yeah, that's actually a good point regarding the CFRP and metal stack materials, right? Mm-hmm. So basically, if we only consider the CFRP and metal in the FDM, I think that's impossible, because FDM cannot print the metal on the top of CFRP. Whereas if you are considering we just manually, put another, thin layer of metal sheet on the top of CFRP, we have to consider how to bond these two parts, because CFRP and the metal will have a very poor bonding if there's no post-processing methodology, right? We may have to think about use a laser to heat the metals and then somehow generate the heat at the interfacial region, so that the underlying CFRP could be partially melted, and then the metal could be bound with the previous CFRP. So that could be a possible solution. And later on, print the CFRP on the metal again, so that it could be a, stack materials in that way. But this is only a potential way to do that. I think there will be a lot of challenges recently as well for, a lot of scholars are working in this area, how to improve the bonding behavior between these two.
Okay, thank you.
Yeah, thank you.
Thank you, Dr. Ning. And we have one last question about the effect of part size on the properties.
So again, is the particle size or part size?
It says part size. I'm not sure if it's part or particle. Maybe it's particle.
Well, let me check. Just make sure I understand the question correctly.
It's the very last one in the chat.
Okay, it's a part size on the property. Yeah, so actually, you know, for the, let's say the tensile property, we have to follow the standards, right? The standard will come up with the dimensions in terms of the size. So what we did is just utilize the standardized part size for the testing. But of course, you can change the part size and to investigate what's the effect on the property, but I will expect to see very few effects on the part size because, you know, for example, the tensile strands evaluate the loading by the cross-section area. So the part size will have very few or little effect on that, I believe.
Yeah, thank you very much, Dr. Ning. I think we're almost at the end of the presentation. We have one comment from Dr. Mohan Kumar, thanking you for your work and saying that your work is very interesting. And it's very interesting and to work with you on simulating the resin continuous fiber flow. And he will follow up with you via email because they have an FDM simulation at VIT. So that's great. This is definitely, you know, some of the outcomes of what we're hoping to accomplish from this joint webinar is to encourage collaboration between our colleagues at VIT and our colleagues here at Binghamton University in the broad area of advanced manufacturing, material science and engineering, and other domains. So I'm very glad to hear this feedback from Dr. Mohan Kumar.
Yeah, sure. Thank you for your comments. And I also look forward to the future potential collaboration. So just feel free to send me email if you also have interest in this research area. Thank you.
Thank you. Dr. Fuda Ning, if you don't mind, maybe you can type your email address in the chat. This way, Dr. Mohan Kumar and possibly others will have access to it, if you don't mind.
Yeah, sure.
Greatly appreciate it. And this concludes our session for today. And at this point, on behalf of Binghamton University and our colleagues at Vellore Institute of Technology, I would like to acknowledge Dr. Fuda Ning's contribution to this webinar series. And thank you very much for joining us and for delivering this first talk on additive manufacturing with all the expertise that we have on campus and some of the ongoing research activities. And hopefully this will inspire additional research collaboration in the future. So thank you very much again, Dr. Ning, for participating in the seminar.
Thank you.
And at this point, before we conclude, I'd like to thank everyone for joining us today as part of this seminar series. And I would like to invite you to join us next week for the next presentation, the 6th presentation of this joint webinar series. We are delighted to have Dr. Nirmala Grace from VIT. She's a professor and director for the Center of Nanotechnology Research at VIT. And she has kindly accepted our invitation to participate in this seminar series. In fact, you know, I worked with Dean Vasudevan, Dr. Brajesh, and Dr. Nirmala Grace to put together this webinar series. So we're delighted that she will be speaking next week about some of her research activities. This will be next Thursday at the same time using the same registration link. Again, if you click on it, it will auto-populate all your information and you will be able to register in a matter of seconds. And we hope to see most, if not all of you next week as part of the seminar series. And as a follow-up, later today, I will send an email with the recording of this seminar by Dr. Fuda Ning, and then send you the abstract for Dr. Nirmala Grace's presentation. Thank you again, everyone, for your participation, and look forward to seeing you next week. Thank you again to our colleagues at VIT. We wish you a wonderful evening, and thank you to our colleagues in the US, and have a wonderful day.
Thank you.
Thank you very much, Dr. Ning and Muhammad, for your great support. Thank you so much. We'll see you next week.
Thank you, Dr. Mohammed and Dr. Ning. Thank you.
Thank you.
Thank you, Dr. Bruce.